Okay, let's consider the example of the class activity today. Okay, we're starting with the initial value problem of this equation. We have this equation. We have ordinary differential equation like this. Okay, this equation is ordinary differential equation, first order and linear. Okay, so because this is a linear equation, we can solve for the exact one. We can solve for the exact one. It's the linear. Okay, for the exact solution, we may starting first for the exact solution. Because it's a linear equation, we can use the separation of variable to solve this equation. For the exact solution, you have to obtain the formula for the function y. Okay, it's not just only the number. You have to have the formula in terms of x. That is we call exact solution. And after that, you have that function to determine for y at each value of x from based on that function, not based on the numerical procedure. Okay, that's we call exact solution. According to this, based on separation of variable, we have the equation of dy 1 over square root y dy equal to 1 plus 2x dx. So we integrate both sides. Then we obtain what? We obtain the solution like this. So it means that we have this equation, right? With one constant. Okay. This constant can solve by using the initial value. From initial value, we know that when x equal to 0, y equal to 1, right? Substitute initial value into this equation, we obtain that when y equal to x equal to 0, y equal to 1. Okay, so what does it mean? It means that c equal to 2, right? So for c equal to 2, it means that we have the equation of okay, so we have this is the solution. This is the exact solution for this equation, right? We keep it because we would like to compare with the numerical solution obtained by fourth order Runge-Kutta method. Okay, now we will use the fourth order Runge-Kutta method to compute the numerical solution for y at x equal to 1 with the step size of 0.5. Okay, so what is fxy? For Runge-Kutta method, what is fxy? Fxy is equal to what? For the case of fxy. For this case, fxy should be what?
1 plus 2x times square root y.
Yes, okay. Don't forget square root y. Okay. because the Runge-Kutta method, Euler method, modify Euler, and Huen method is come from this type of equation. Okay, it's based on this type of equation. So you have to rearrange the equation to be this form first. So for this case, it means that f of y is equal to 1 plus 2x multiplied with square root y. Don't forget this. Okay, but some students forgot that. You just only this. So you obtain the incorrect solution. Be careful for that. First thing that you have to do to rearrange the equation into this form first is maybe better. So from this equation, if you rearrange the equation, you will got like this. Then it should be starting with this. Okay, that it should be reduce your missing. If you keep the equation like this, you may missing some term. Okay, don't forget to rearrange the equation first. Okay, so because it has a limit of time, I will develop the Excel sheet for this case. Okay, but I still recommend you to solve it by hand, by calculator. Okay, but I will show you how to calculate the solution by Excel. Okay, actually this problem just only 2 steps. You see that I define that would like to know y1 rate. The step size is just only 0.5. So actually we can do by hand. Okay, by hand. It just should be enough for 30 minutes. Okay, but right now we will develop Excel sheet instead. Okay, you see that if we use the Excel, if you not prepared before, so it maybe takes more time than solving by hand. Okay, so we starting with x, right? And then we would like to determine for k1. K1 is what? K1 is f x0 rate by 0. Okay, and after that we determine for x1 and y1. x1 is xi plus 0.5 h. Okay, and y1 is yi plus 0.5 k1h. Actually, it's not necessary to remark the formula over here, but because I don't want to switch the slide to I would like to remind myself to the formula. So this is just fx1 y1. That is k2 rate. And after that, we determine for x2 and y2. Okay, this is just should be f x2 y2. And then we solve for x3 y3. And we obtain f x3 y3. It should be k4. And this is k3. Okay, for x2 is what? x2 is xi plus 0.5 h. Okay, y2 is yi plus 0.5 k2 h. Okay, x3 is equal to xi plus h, y3 is equal to yi plus hk3. Okay, that's all. After that, we will obtain the solution. Solution that is y. Okay, starting with the initial value. Initial value is when x equal to 0, y equal to 1, right? And for initial step, it is not necessary to determine this value, right? Okay, and what is the function? This is a function, right? And the exact one, exact solution is 1. This is the exact solution. We will compare it later. Okay, based on the function f(x,y) is over here, right? Step side. Okay, may just create for the general case of step side. Okay, I may set up step side over here. S is equal to, for this case, it's just 0.5. Okay. Actually, you may not necessarily to do like me, because I would like to show you in the final that when we change the step side, what's happened to the solution that we obtain. Okay. So next step for next step is equal to what? Is equal to this plus step side. Okay. And then what is K1? K1 is equal to square root y, right? Square root y, yi, multiply with 1 plus 2 xi. Okay. This is K1. Then x1 is what? X1 is xi plus 0.5 plus multiply with h. Okay, this and yi, y1 equal to what? Y1 is equal to yi plus 0.5 multiply with k1, right? K1 is over here. Okay, multiply with h is over here. Okay, don't forget to lock the cell here. Like this. And after that, okay, for K2 is equal to L x1 y1, that is root of y1. Okay, multiply with 1 plus 2x. Okay, that's it. Okay, for x2 is what? X2 is the same. X2 is xi. Okay, plus 0.5 h. Okay, for y2 is what? Y2 is yi. Okay, plus 0.5 with K2, right? Okay, with h. Okay, after that we determine for f(x2, y2). That's it. We can copy this cell. Okay. After that, we determine for x3 is equal to what? Is equal to x plus h, right? And then for y3 is what? Y3 is equal to yi, right? Plus h multiplied with k3. Okay. For k4, it's the same. Okay. Finally, determine for the solution. Solution is what? Solution is over here, right? So yi plus 1 is equal to what? Is equal to yi plus 1 over 6. Okay, multiply with k1, right? Plus 2 k2 plus 2 k3. Okay, plus k4. Okay, multiply with h. Okay, multiply with h. Then we have this. That's all. If we compare with the exact one, for exact solution, okay, for exact solution, y is equal to what? Y equal to x squared, right? Plus x plus 2. Okay, and square. And is divided by 4. Okay, this is the exact one. So when we compare with the exact solution, we can find the percent error, right? Okay, the percent error as the first should be 0 because it is the same. Or the another value is the comparison between the numerical solution and the exact one. Okay, divided by the exact one. This is the percent error multiplied with 100. We obtain the percent error of 0.03%. Okay, it should be good. It's good enough for the solution over here. And after that, you do the same thing for the step of just only one, right? There's only one. When x equal to 1, solution is over here. Okay. So what do you think for the case of the solution that we obtained here? This is a numerical solution from Lumekutta method, and this is for the exact solution, and this is the percent error. Okay. So if we do the same for the steps, next step until until x equal to 5.5. Okay, actually we should show the decimal just for 6 digits, right? Okay, it's just for 6 digits already, right? Okay, you see that when we do it again until x equal to 5.5, okay, the comparison between solution of y obtained by Lumekutta method and exact one, it just close also, but with some for this case you will see that it has the error just first digit, but you have to compare with the significant figure instead. For the significant figure, you will see that for the significant figure, it should be this term time 10 minus 3. Oh, sorry. Okay. You see that it just with the fourth digit, that it should be error for this case. Okay. So if we reduce the size, oh, what's happened? Sorry to this, it should be okay. If we reduce the step size, you will see that the solution is better, right? It's better. Okay. This is all for the Lumekutta method. Okay. This is all for Lumekutta method. Do you have any question for this?